Here's the Earth, all well separated, with all of the metals where they're supposed to be in the core. And then this planet was salted with meteorite debris that brought metals with it, including gold. That's the surprising conclusion of the origin of gold to Earth's surface.
Even though the planet had a new supply of gold, there wasn't anything to see because it was just too dilute. The gold that there was a tiny fraction of the Earth's crust, and it was spread out around the planet. It was really rare. And yet, billions of years later, a human could just pick up a nugget of gold out of the landscape. To get from one to the other, the planet had one final trick to play. With only 1 gram of gold for every 1,000 tons of the Earth's crust, there had to be a way to concentrate the tiny particles of gold into the colour we see today. And across the surface of the planet is something that can do just that. In the streams around Jamestown, prospector Brent Schock relies on the properties of water to seek his fortune, just like the original gold rush pioneers. In doing so, he's mimicking the planetary processes that finally brought us gold.
Just sprinkle over here.
So this is just dirt from the side there?
This is it, yeah.
So it's like a little ladder here and the stream's bouncing over the ladder.
That creates a low pressure area. Water slows, gold drops.
Yes.
You've got your crevices here. You've got your low pressure areas there with the riffles. And if it's dancing a little bit, the gold can work its way down. And they will grab hold of the fine gold.
So it's getting caught just behind these ridges.
Mm-hmm. Exactly.
And then you just look through this and look for the colour?
Yeah, we look. We don't put our fingers in.
I really don't. No. That's me told, isn't it? So this looks really simple, but actually there's a very sophisticated thing going on here.
You're the scientist.
The stream can replicate naturally this setup here.
Yes. Constantly eroding, constantly rising and settling. Every time the water rises and then starts, you can come out here and find gold laying on the bedrock. Almost a renewable resource.
So we keep shoveling this stuff in.
You want to look at the gold. Is it coarse? Is it smooth? The smoother it is, the farther it's traveled. Then you want to triangulate your way up and find out where the vein is, where the source is. That's what everybody wants, the source of what's feeding this.
Over millions of years, water picked up gold, transported, sorted, and concentrated it, and then deposited it in a form that made it easier for us to find. It's a process that's still happening and drives our continued obsession with one of Earth's most alluring colours. This spectacular colour has been on quite a journey. These atoms have travelled from a distant star in time to be there for the birth of the solar system. And then they hit the Earth in an impact which left a golden signature on our landscape. And even then it didn't stop because there were sorting processes, first by geology and then by water, until humans could pluck nuggets like this from the landscape. And still it carries on because there are atoms from Egyptian jewellery or Inca trinkets that are almost certainly part of modern wedding rings or gold bullion. So the cycling carries on, but this fantastic colour stays exactly the same. I'm about to enter a very different world. David Margolis is an artist, historian, and devotee of the colour blue. In his London studio, he works with some of the rarest minerals and pigments on Earth. Among them all, the most spectacular are the blues. And one blue in particular takes pride of place on his shelves.
This is a piece of lapis lazuli that's come from the one mountain in Afghanistan.
So the important thing here is this blue colour, and that is lapis lazuli.
It is. It was the most precious and most expensive of all the pigments.
There aren't many blue things in nature, so this must have been a spectacular thing to display and to find.
Someone had walked through the mountains of Afghanistan and come across blue stone, and it makes me wonder whether they believed that the sky had fallen to the earth and turned to rock.
I love that idea, the sky that had fallen into a rock. That's exactly what it looks like, isn't it? The colour is so stunning. I can imagine the impact it must have made when lapis first arrived in Europe, when trade routes from the east opened up.
It was seen as extremely valuable. In Renaissance Italy, it was so expensive, it was the equivalent of the price of gold.
To have this was a status symbol, and the most visible way of having it was to put it on a painting, because you could paint this colour onto a big canvas and show that you had this commodity. So it's not a subtle way of displaying your status. It's saying for everyone to see.
I don't think it's subtle at all. I think the most important aspect is that lapis does have a slightly mystical quality. So when it came to painting, quite often the blue was used to paint the robes of Mary. Probably the most famous artist to have used it is Titian.
There's something entrancing about this colour. But to discover what it can tell us about our planet, I need to do what painters do and get right inside this rock. An artist is presented with a lump of this rock and they have to make paint out of it. What do?
They hammer it.
Not very sophisticated.
Hammer it until it gets smaller and smaller.
It was quite satisfying, this. This is the first time it's been a colour, because this has never seen daylight before. That bit of rock I've just smashed has just become a colour for the first time. So the next one along, so now we've got lots of broken up little bits. And you can start to see
Some
blue powder.
That's right.
And that's what the pigment is, it's the powder
Yes.
when it becomes a powder.
That's right.
Oh, that's a horrible noise. It's such a horrible noise.
And you might smell it as well.
Oh, there's a really strong smell of sulphur.
It is sulphur. Sulphur is what makes the rock blue.
And then the final stage, when it's broken down, is what we've got in the last one here. This is the bluest thing I've ever seen. It's the chemistry of this rock that creates its colour. Sulphur more often produces yellowish compounds. This is lovely, lovely stuff. But in lapis lazuli, the unique combination of sulphur with other elements produces this deep, rich blue we call ultramarine. And this is it. This is the final step. The blue powder has been mixed with oil and some wax, and it's a paint. And so this rock that looks like it fell from the sky is becoming sky all over again. When we look at this, we just see a blue rock. But the secret to that colour, it's hidden in the atoms that make this up. But the atoms themselves aren't enough. To get this, you need to transform them. For a transformation to this dramatic blue, you need the sorts of pressures and temperatures with which planets are forged. This map shows how UV varies across the globe.
Throughout Africa, there are these very high levels, but the levels taper off dramatically as we begin to get into Western Europe or Eastern Asia.
And in places with less UV, high levels of melanin created a problem.
There are some wavelengths of UV that are actually essential to our health, that promote the production of vitamin D in our skin.
We need vitamin D for a strong immune system and healthy bones. But with less exposure to the sun, our ancestors couldn't make enough of it. To survive in these new lands, our colour had to change. Nina has produced a map that shows how human skin colour adapted.
You see very darkly pigmented people that are concentrated in the areas of high UV, and then much more lightly or depigmented people as you get closer to the poles under conditions of very low UV.
So each population works out a balancing act. So they're protected enough that their DNA is okay, but they still have enough UV to make vitamin D.
Precisely.
This interaction between our skin and the sun is so finely balanced that even in a single individual it can adapt and change. To show us, Nina is looking for the people with the biggest difference in colour between parts of the body that get a lot of sun exposure and parts that get very little.
So let's look here. Now we don't see a lot of difference here between your upper inner arm and your forehead. They're pretty closely similar. And with the two very lightly pigmented people, there's very, very little difference. And similarly, at the very other end of the line with our most darkly pigmented person, there's very little difference.
But in the middle of the line, things are different.
So if we look at some of these individuals, the difference is really quite great. The unexposed skin versus the exposed skin, we can really see a visible difference. And all of these people have sort of moderately to darkly pigmented skin, and they have tremendous abilities to tan.
Tanning is the solution to living at latitudes where sunlight changes dramatically throughout the year. In these regions, people produce melanin to protect them in summer and then lose it in winter. All of this suggests a problem because today we jet all over the world, we live in countries which we weren't born in. Does that cause problems?
Now we have to modify our lifestyle. We have to think about whether we protect our skin from ultraviolet radiation or whether we take vitamin D supplements.
It's only recently we've been able to take measures like this to help control our relationship with the sun. For most of our history, this vital role was played by our own skin. We humans have got loads of words for red. Vermilion and ruby, scarlet and crimson. And it strikes me that all of those words imply something that's bright and deep and rich. For us, red is the colour of love and the colour of war. It can scare us, and it can worry us, and it can move us. But red isn't significant only to us humans. It holds a special place across the living world. To discover why, I've come to meet Andrew Smith, a zoologist at Anglia Ruskin University. He's working with New World monkeys like these marmosets. Some individuals in the group can distinguish the colour red, others can't.
Marmosets have got a slightly strange system of colour vision. All of the boys are red-green colourblind, along with about a third of the females. And the remaining two-thirds of the females see the world in a very similar way to ourselves.
So within the same troop of monkeys, some have colour vision like ours, and some have red-green colour blindness type vision, and you can directly compare the difference.
Yes.
To discover the difference it makes if you can distinguish red and green, Andrew has set the monkeys a challenge. And I'm going to give it a try.
I've got a pair of glasses which will transform your vision from normal colour vision to, if you like, colour blind vision. So if you'd like to put them on. We've put some strawberries in the tree behind you. We've got some ripe and some unripe strawberries. And I'd like you to find all of the 7 ripe strawberries as fast as you can.
Ready to go?
Okay, go.
The world's gone very green. With the goggles on, I see the world as the colourblind marmosets do. There's one.
The ripe strawberries look very black here, so it's quite hard to pick them out against the dark trees and the dark background.
Under here? Oh, there, right, I was looking too far forward.
All right, so have I done the job? Seven strawberries, 7 ripe strawberries.
Perfect, you found them all, and that took you 1 minute, 10 seconds.
Andrew resets the tree with fresh strawberries so that I can try again, but this time without the goggles.
Okay, go.
This is much easier. 2, 3.
My natural colour vision is very similar to that of the female marmosets that can also see red.
6, 7.
Fantastic. 16 seconds. Yeah.
Huge difference.
So that's an awful lot faster than the 1 minute 10 that it took you when you couldn't tell a difference between red and green.
Andrew's been carrying out experiments like this on monkeys to see how colour vision affects their ability to find ripe fruit.
There's one just in the background there having a bit of a look.
No, here we go.
Yeah, this one's seen it. That one is sitting right on top of a ripe strawberry and not noticing it at all.
After repeating the test hundreds of times, Andrew found a clear pattern.
What we found is that all of the monkeys could do the task given enough time, but the monkeys with human-like colour vision went straight for the ripe fruits.
In the wild, being the first to find the food gives you a huge advantage. It can be the difference between life and death.
This plane started life as an ordinary passenger jet, but these days it's something really special. And I'm really excited because I'm going to get to fly with it on its next mission. Like any other aircraft, it's going to take off from an airfield, and like any other jet, it's going to go up through the weather to the top of the first layer of the atmosphere. But then it's going to keep going up into the stratosphere, above almost all the water vapour. At that point, the back of the aircraft will open up, and what will be revealed is a telescope capable of looking at the richness of the universe in the infrared. And I will be closer to the stars than I've ever been in my life.
Meet Sophia, the Stratospheric Observatory for Infrared Astronomy.
So here we are, ready to go. There are 25 people on this aircraft. The crew and the scientists are all back there doing the last preparations. And I'm really excited about 2 things. One is that we're going to fly around the back of the planet in the dark, looking out at the universe. And the other one is that I have never had this much legroom on a flight in my entire life.
45, 50, valves closed, 610, 610, 10 degrees warmer from last.
Right now, we just left Nevada, and we're just abeam Salt Lake City right now.
Oh, so Salt Lake City's right over there.
Salt Lake City's right there.
And you do have the best view on the plane.
It's the greatest view in the world. This is the best job in the world.
That's the pilot's privilege,
really
isn't it? To look out at the sky.
It is. The higher we go, the better the telescope can see, for lack of a better term. And because there's less moisture in the air, the higher we go.
Well, the 700 pounds for over altimeter 299.7.
We've got the mission director, so this is the science heart of the mission. This is where the decisions are being made. And this is the science ops. So the chief scientist, people who control the science ops, are sitting here. They're looking right at the telescope. They've got data on the screens. You can see the constellations that they're following.
It's the beginning of another long flight for Sophia's science operations manager, Dr. Jim DeBiser.
Tell me why infrared astronomy is worth all of this effort.
There's a lot of dust and gas between us and a lot of objects of interest. Stars, when they form, for instance, are completely enshrouded in their natal cocoon of dust and gas. The infrared allows us to peer into that and look at what's going on at the center of these star-forming regions and actually find out how these stars form. I like to use the analogy of a car's radio and a GPS. You can go into a tunnel and you can't get a GPS signal anymore, but you can get a radio signal. And that's because a radio has a much longer wavelength. So when we're looking into space, going to longer wavelengths like the infrared allows us to penetrate into areas and see things that we can't see in the optical. We're observing the invisible.
To begin to explore the hidden world of ultraviolet, I'm meeting Ron Douglas, Professor of Visual Neuroscience at London City University. And some very friendly birds.
We've got starlings here who are eagerly pecking away at the food we've got for them.
Starlings have a special relationship with UV. Their eyes can see this colour, and some of the female birds' feathers reflect it. I'm intrigued to know why.
They are actually very, very sensitive to UV. They have photoreceptors that respond in the UV, and they also have lenses at the front of the eye that let the UV through. So they really are true experts at UV vision.
And what is it that they're looking at? What can they see with UV vision?
Well, when it comes down to it, for most animals, life is really about two things. It's about food and sex. Perhaps UV reflecting female starlings are attractive to male starlings, because female UV reflecting starlings, they have much bigger brood sizes. They're more effective at having young, so that must mean they're more effective at attracting the male starling.
Now we've got a mixed group around us, both males and females, and I can't tell the difference between them just by looking at them.
Some of the bits of their feathers reflect ultraviolet light. Of course, we're completely unaware of that. But they are attracted, in part, to the ultraviolet colours.
So there's no excuse at all for thinking that the world is the way that we humans see it and that we have the best vision of all.
No, absolutely. In most respects, we have inferior vision to a lot of animals. So we've seen that we don't see ultraviolet light, but a lot of animals do. In fact, for every aspect of vision, you can pick out an animal and it does it better than us.
One creature that's long had a reputation for superb eyesight is the eagle. Meet Sasha.
Ron, we've got quite a noisy eagle here. He's talking away to us. And he's having a good look at everything, but he's not seeing the world in quite the same way that we are. What's different about his vision?
His ability to see detail is about twice as good as ours. It's like having more pixels in your camera. The more pixels, the higher the quality of the image.
Until recently, it was generally thought that all birds of prey had UV vision, and that this made them better hunters.
There was a very nice story going around that raptors in general could follow the urine trails laid down by small mammals. Since urine reflects ultraviolet light, it was thought that raptors could probably find voles by following the UV reflection from urine trails. Sadly, that seems not to be true. And it's not really true that he doesn't have the photoreceptors to see ultraviolet light, but he actually puts a filter in his lens that cuts out most of the ultraviolet light.
On the face of it, ultraviolet sounds as though it should be extremely useful to a top predator. But there's a reason Sasha doesn't make use of it.
The one thing we do know about birds of prey is that they have amazingly keen eyesight. They're really good at seeing fine detail. Now, a problem with ultraviolet light is it's scattered more than other wavelengths, so ultraviolet light gives you poor images.
As a bird of prey, the last thing you want when hunting small animals is a lot of scattered light and a blurry image. And that's why Sasha has a lens over his eye that filters out the unhelpful ultraviolet. we humans have also evolved to filter out UV, both for visual acuity and protection.